Ora si registrerà la conferenza.
Can you hear me from online? Is the audio clear?
Yes.
Okay, thank you. So today, Monika Feldmann is with us. She's a friend and ex-colleague from Bern, working in the group of Olivia Martius. And she had a PhD from the University, from the Polytechnique in Lausanne a couple of years ago, I believe, a year and a half, working on supercell detection and climatology. And she's been visiting the US intermittently since her master's, right? So you've been collaborating with storm people from the US as well. And yes, she's an expert on storms, so on convective phenomena. And this is the wide topic she'll talk about today. So the word to you, and if there's any problem from online, just talk to us and let us know. Yeah. Yeah.
It's working great. I will move myself over here so hopefully I don't block too much of the screen. And I guess I need to turn the camera on this one.
No, the camera is from my TV.
Oh, it's from this one. Okay, perfect. Okay. Thank you very much for the introduction. And yes, with this, I will pretty much jump straight into the subject. I will be talking about different aspects of thunderstorm predictability today. And here tying together two different projects, one focusing on artificial intelligence-based forecasts, so really coming from global AI-based weather prediction models, and then also talking about large-scale drivers and how they relate to severe convection. And yes, as Alice said, I work in the Climate Impact Research Group at the University of Bern. Nonetheless, I want to start with an introduction to thunderstorms overall, since not everyone works in this subject, and I will cover a few introductory things in these first few slides. So, diving into the necessary meteorological ingredients for thunderstorms first, the thing you basically need the most is heat or a form of buoyancy, which gives you an unstable atmosphere so that you can have vertical motion, basically convection setting in. This is assisted by moisture, so just for having the vertical motion of convection, you technically don't need moisture, but naturally latent heat release will increase your buoyancy as well and your vertical motion. And naturally, we mostly associate rainfall with thunderstorms, so while dry convection is possible, we usually associate this with a very humid atmosphere that leads to precipitation on the ground. And then not necessary requirement for thunderstorms, but for thunderstorm severity is wind shear, and this is the differential wind vector between the surface level and approximately the mid-troposphere, and the wind shear directly determines how organized a thunderstorm will be, which then directly relates to its intensity and impact. And then the final thing you need is some kind of trigger. Usually you are not absolutely unstable in the atmosphere, otherwise you would have overturning convection absolutely everywhere, but you need some kind of small mechanism that will jumpstart this and overcome the convective inhibition. Talking about instability first, sorry, here we go. The term we use most is called convective available potential energy, and it basically relates to the energy that is released in the ascent of an air parcel once it rises freely. So once you have an air parcel that is warmer than its surrounding air and it starts having a vertical motion, and while it rises it will cool, but is cooling less than the environmental temperature and keeps being warmer, the energy released here is what we call K. And this is determined by both the temperature and the moisture profile, as once you're cooling, once you reach saturation, you will additionally have the latent heat release of condensation. We commonly assume that thunderstorms start from a few hundred joules per kilogram Cape, but values go up to several thousand joules per kilogram Cape, typically having a global maximum somewhere around 6,000 joules per kilogram. In Europe, not so frequently above 2,000 joules per kilogram. These really extreme values stem more from the Great Plains of the United States. Then having wind shear next, so this determines the convective organization, and we usually use the bulk shear, so the differential wind vector between the surface level and approximately 6 kilometers. If we're working with pressure levels, often the 500 hectopascal level. If this speed difference is less than 10 meters per second, we get single cell thunderstorms, which we will look at on the next slide, but it's basically your standard summertime thunderstorm that just pops up and falls down again. Between 10 and 20 meters per second, we get multicellular thunderstorms where one storm triggers the next and gives you a more widespread form of convection. And then starting from 20 meters per second, we get supercell thunderstorms, which are a very organized type of single cell thunderstorm that basically has an in-storm dynamic that reinforces its own lifetime, which we will also look at on the next slide. So here we have the life cycle of a single cell thunderstorm. And we start with the cumulus stage where you have convection setting in, you have vertical motion, and the cloud starts growing vertically. And then in the mature stage, you have reached the tropopause, you start having an overshooting top, but you also have precipitation forming. And this precipitation basically falls down into the updraft, effectively cutting off the storm. So in the dissipating phase, you basically have the storm terminating its own life cycle in that it falls into itself. And this is determined by having so little wind shear that the top of the storm is basically at the same location as the bottom of the storm. There is almost no tilting, which means that the precipitation falls down into the updraft. In a multi-cell thunderstorm, we already have a bit of a bigger shift and tilt of the system, while each single cell will still dissipate within one life cycle of this cell. The outflow is stronger and is displaced from the storm, which leads to this outflow triggering a next cell. So in multi-cell settings, you often have a succession of thunderstorms where you see several next to each other that are all in different stages of their life cycle. You will see a dissipating one next to a mature one next to a cumulus stage of a thunderstorm, and this will lead to a larger area that is impacted as well. And then coming back to the supercell thunderstorm, as you can see, it has quite a number of distinct features. What we often talk about is the rotating updraft, which is called the mesocyclone. And this is really from the shear profile in the atmosphere. This gives you horizontal vorticity, so a component of rotation that the updraft tilts into a vertical component. And this, on the one hand side, gives you a pressure deficit that increases the updraft again, but also allows the storm to propagate by having the pressure deficit slightly deviated from the actual center of the storm. It's usually displaced to the right moving supercell to the front and right. So bringing the storm motion forward, and these are usually also the fastest moving storms. They have the largest horizontal extent for a single type of storm. So unless we're talking about conglomerates of many thunderstorms, this is the largest and fastest moving system you will encounter. And it also comes with the highest impact, having areas of heavy rain and hail. They have the potential to form tornadoes, and in northern Italy is basically the European tornado hotspot. It will not be it's not what we mostly focus on in European research because it still remains one of the most rare phenomena. So tornado research is usually more focused on the US. However, Francesca here has done really nice work on northern Italian tornadoes. Yes, and then just to round this off, here we have a thermodynamic diagram where we can identify Cape and shear. This is from a tornado outbreak in the United States, and in the thermodynamic diagram, when we have the temperature curve marked here in red, and the parcel profile of an ascending parcel in the orange line, what gives you the Cape value, so the potential energy release, is this area in between the two, this vertical integral. And the parcel profile is also determined by the moisture. So when you switch from the dry to the moist adiabat, is determined by moisture, which really impacts the location where you switch to the steeper slope. So depending on where you switch to the steeper slope, this will strongly impact your final Cape value. And then for the vertical wind shear, looking from the 0 to the 6 kilometer level, here we have about 35 meters per second shear, so we're well above the 20 meters per second threshold for supercell thunderstorms. And we even have very high levels of shear in the 0 to 1 kilometer level, almost reaching the 20 meters per second in the 0 to 1 kilometer. So this is not just an environment that supports supercell thunderstorms, but also specifically tornadoes, which require a lot of low-level shear. And this is a case that will appear again later in this presentation, so just to keep this in mind. Then the last bit that we need for thunderstorms is convective initiation, so you basically need a trigger mechanism to overcome convective inhibition. And frequently this will happen with orography, especially in Europe, where many of the thunderstorms cluster around mountain regions. We have a lot of orographic triggering, but also land surface differences or convergence zones, and also frogs can contribute to overcoming this initial hurdle to starting convection. Then for convective hazards, starting with hail, this requires a strong and wide updraft of a storm. So where in the environment variables, we would look for elevated Cape and some degree of shear, but often really high shear is detrimental to the formation of Cape, with some hypotheses stating that a high degree of shear will lead to hailstones being ejected from the updraft before they can grow very large. But you do want a certain amount of organization in the storm so that you have a long sustained updraft and not just a single cell thunderstorm. Downbursts are very strong winds that come down from the mid-levels, and this usually requires dry air in the mid-levels, which will contribute to evaporation in the storm, which locally cools and leads to a very fast downward motion. Lightning is naturally also a convective hazard. It's most prominent in the mixed phase, and interestingly, most often an underestimated hazard in non-severe storms. So many lightning incidents are actually related to rather weak storms when people assume it's still safe to be outside, whereas in any lightning situation, it is unsafe to be outside. And then coming back to tornadoes, they require a high degree of low-level shear. They're usually tied to a supercell or a mesoscale system. You need the deep shear, so the 0 to 6 kilometer shear for the organized severe storm, and then you need the low-level shear for the low-level rotation of the tornado. After having had this introduction, we will jump into the first part of my presentation, which focuses on deriving convective outlooks from global AI-based weather models. And to motivate this, global AI-based weather models run extremely fast. You can get a 10-day prediction within minutes if you're running it on a GPU, and I think it takes about an hour if you run it on a CPU, which is basically you can run it on your own laptop. So this is computationally very cheap, and we just want to see, can we obtain reliable Cape and shear from these global AI-based weather models? And the article corresponding to this was published yesterday, so feel free to look at that in case you are interested in more details. And we will do most of this work with a case study of a US tornado outbreak. Yes, let's dive into that. And this work was done in a collaboration with the University of Lausanne with the group of Tom Buchler. As a brief introduction to AI-based forecasts, we use a number of different models here. As AI models, we use PandaWeather, GraphCast, and ForecastNet, which were basically the three first released global AI models. And then as a reference, we use ECMWF's IFS, and as a ground truth, the ER5 reanalysis. The AI models are initialized with a multivariate field at the time t0. This can be either ER5 or the IFS real-time analysis. And then you integrate them forward in their prediction time step, which for most of them is 6 hours. And you will keep iterating these 6-hour predictions. So you do a 6-hour prediction, feed that back into the model, do another 6-hour prediction, until you end up at your desired lead time of n times 6 hours. And you receive the same multivariate field that you put into the model as an output at your desired lead time. Tangle weather works a little bit differently. It has several prediction time steps of 24 hours, 6 hours, and also a 3 and a 1 hour model, so you can get a lead time precision of up to 1 hour. And it will stagger together the combination of these models that will give you the least number of integration steps, which reduces the error, but introduces artificial artifacts from mixing independent models. So for a 2-day and 6-hour forecast, it will use twice the 24-hour model and 1 time the 6-hour model. And at the point in time when it switches to the 6-hour model, you have a completely different prediction system. And also, if you look at the difference between an 18-hour forecast, which is 3 times the 6-hour model, and the 24-hour forecast, which is 1 time the 24-hour model, these two are often quite different, and you will have a drastic jump in model behavior when you switch between the 6 and the 24-hour models. So why are we trying to get convective parameters from global AI forecasts? As a point of relevance, severe convection is one of the most costly weather hazards, and as we were discussing the hazards before, these are pretty impactful, with particularly hail contributing to some of the most expensive weather events worldwide. But also, this is a challenging forecast task. So most of these models are evaluated on 2-meter temperature and Z500, and they are evaluated independently on this. So you have single variables on 2D levels, but there is no control of do separate variables match each other, or do you get a correct vertical profile. And for CAPE and shear, we need a correct co-location of thermodynamic and kinematic variables. So we need temperature, moisture, and wind speed that are in the right location, in the right vertical profile, and at the right time, of course, as well. So you are compounding many more factors than was done typically beforehand. In the study, we will be mostly focusing on CAPE, also with the most unstable CAPE. So depending on the altitude, where you launch your parcel profile, you can get different CAPE values, and we basically just take the highest one that you obtain. And then we also do a combined CAPE shear variable, which is called W max shear. Also important to note, the models have a vertical profile given in pressure levels, and if we look at the profile here on the right-hand side, the wind bars denoted here in black is the accuracy that you get from pressure levels, as opposed to ERA5 model levels, which is the medium one in gray, or an observed sounding, which is the light gray one. So we have a considerably reduced vertical resolution than an actual numerical weather prediction model. But to be fair, with the comparison, we apply the same constraints to everything, so everything is evaluated on these coarser pressure levels. The case we're looking at will be the 12th and 13th of April 2020, where we have a convective outbreak at the leading edge of a trough. And we here see the temperature anomaly over the US during this time. We can see it's a very warm anomaly going up to 10 degrees above the climatological norm. And also the Gulf of Mexico was very warm at this time. This led to an environment with quite high CAPE values, especially for the time of year. In the end, April is really the beginning of the convective season. And we see here the CAPE field, as well as overlaying the deep layer shear field with shear values going up to 50 meters per second. So really exceeding the requirement for supercell thunderstorms. Warnings were issued 4 days prior by the Storm Prediction Center, and ultimately what happened was that 141 tornadoes touched down in 10 states, leading to 38 fatalities. So what we see in the bottom is, for one, the warning polygons drawn in the shading that were issued several days prior, but then also the storm reports of the day. These are the real-time tornado warnings that are issued as tornadoes touch down, and all of the triangles are confirmed tornadoes, and we have this really widespread tornado activity over these days. When we are using the AI models, however, we are not predicting the actual tornado occurrence. We are more interested in this kind of porous polygon drawing, because we are only looking at the prediction of cape and shear, and we are not actually looking at the storm scale. AI models also largely don't contain precipitation, so they don't actually contain any kind of storm. It's just a representation of the atmospheric state. So here we have the time step 12 UTC on April 12th, which is just before the first tornadoes start. And this is the time step we will first focus on first for forecast evaluation. Also taking another look at the accuracy of capes that we get from pressure levels. We looked at the comparison of ERA 5 cape from pressure levels and compared it to ERA 5 cape from model levels. And the density diagram is depicted here, and what happens is that you squash the distribution of it. So we overestimate low values, but we also underestimate high values. So you basically, if you would fit a line through this, you would go from here overestimating to here underestimating. And then if we compare this to soundings, we are actually always underestimating. So ERA 5 is systematically underestimating cape when you compare it to the cape found in soundings. So just as a perspective on what forecasters would desire to have, which is naturally the observation, and what we are working with here. We first look at the lead time of 12 hours here for April 12th at 12 UTC. And the reason why we look at such a short lead time is we wanted to figure out first, do we even end up in the right order of magnitude? Does cape make any sense when you derive it from AI models? And at the 12-hour lead time, we can see that IFS produces a quite similar field, a bit overestimating the area, but also with a high degree of detail. And then when we look at the AI models, I was very positively surprised that we do end up in the right order of magnitude, and the shapes honestly also look quite similar to ERA 5. We do have less detail in the data, so the information resolution seems to be less fine than ERA 5 or IFS, but this kind of blurring is also something quite known from generative AI that doesn't give you as sharp features. When we look at the difference between the ground truth and the models, we can see that overall GraphCast leads to the lowest errors here. So IFS is actually penalized for its high degree of detail, because if your detailed feature is not in the right location, it will lead to a large absolute error. And what we see here as well is that ForecastNet is underestimating the event by quite a bit. Then if we go to a much longer lead time of 7 days, the thing we see first for IFS is you see a big displacement error, and you could argue this is just a spatial error, but I would say it's a time error and propagated the system too fast. So the time step when the system looked like this is more like a day later. So basically IFS was just a day too fast in its event propagation. Then Pangu weather is losing a bit its the correct shape here. The orientation of the track doesn't appear to be correct anymore. GraphCast is still decently similar, and ForecastNet is quite strongly underestimating the event at this point. But we still end up in a relatively reasonable value range, which I found very encouraging. We're not going outside of the reasonable value range. The models behave quite stable. Here we also have the delta plots, and especially for IFS, you can see that if you would just compute a root mean square error on this field, this will be extremely large and actually larger than any of the other three models just by the displacement of the field.
Is this an ensemble forecast?
No, this is just a deterministic run. And all of these forecasts are deterministic, so none of these models are yet run in an ensemble mode, but that is an active field of research. They're really struggling to get ensembles dispersive enough. Right now, they're very under-dispersive and less dispersive than the numerical ensemble, which is also under-dispersive for what you would actually want. So a case study is well and nice, but we cannot trust a single case study. So we looked at the entire North American convective season for 2020, and looking at the root mean square error first for Cape for the different lead times. This is the graph that we get, and we see that GraphCast, HangoWeather, and IFS achieve very similar scores to one another, and ForecastNet appears to be an outlier with having much higher errors, and we will look at why in a second. Another thing we see is that we have a strong diurnal cycle of the error of Cape. I isolated here the initializations at 0 UTC, so you can really see the diurnal cycle, this 24-hour oscillation. And the error in Cape tends to be large at times of day when Cape is large. So during the late afternoon local time, you will have greater errors on average. And I was also quite impressed here that in spite of the difference being small, you do see that GraphCast has systematically the lowest error. The interquartile ranges of these models overlap, but the median is systematically lower for GraphCast than for HangoWeather, and for HangoWeather lower than for IFS. But to be fair, this is the metric they're trained on, so this is the metric they will perform best on, and you should always evaluate on other metrics in addition to that. The next one we look at is the bias, and now we can see that ForecastNet is in fact overestimating Cape to quite a large degree. And this is the complete opposite to the case study. So with this, I just really want to highlight that a case study can really distort the picture of actual model performance if your case study is not representative of the climatology. And this being a very early convective case was not representative of the climatology. Then we also looked at the fractional skill score, which shows the fraction of a 1 degree area where Cape exceeds 300 joules per kilogram. And here we start to get a bit of a more heterogeneous picture. So we no longer have the very strict staggering of GraphCast is better than HangoWeather is better than IFS. So you start seeing that when you allow for a bit of displacement error and you're working on a binary threshold, you no longer get this clear staggering that is partially owed to metrics being used in model training. Then we also went into more meteorologically oriented scores. So the SAL score is a score that was developed for precipitation and evaluates patches, usually of precipitation being greater than 0. In this case, we evaluate patches of Cape greater than 300 joules per kilogram. And the structure score looks at the scale of features. The higher it is, the more you are blurring features. And if it is negative, then you tend to have too small features or too finely detailed features. So as expected, IFS scores the closest to 0 here, and the higher values of the other models indicate the blurring, and it also tends to increase with lead time. The amplitude score is similar to the bias, and here we also see much the same story as for the bias, and then the location score evaluates the overlap and centroid of the patches, and the models are very similar apart from ForecastNet. And it is important to say here that if your model is performing very badly overall, these scores tend to be bad in relation to one another. If your structure is completely wrong, you cannot determine the location correctly anymore. If you're basically overestimating the field to a point where you just have one large blob of 300 joules per kilogram Cape, you cannot estimate a correct location that will be similar to the other models. So what impacts performance? And one of the striking differences was ForecastNet predicts relative humidity, whereas the other models predict specific humidity. And to compute CAPE, I need to use specific humidity. So one question was, does the conversion from relative humidity to specific humidity introduce additional errors? And to figure this out, we computed relative humidity and specific humidity in all models and compared these. What we can see is that for relative humidity already, ForecastNet has a worse root mean square error than the other models, in spite of the other models having undergone the conversion here. Then when we go to specific humidity, this separation increases, and basically ForecastNet is penalized for A, having a bad relative humidity prediction in the first place, and B, then converting that bad prediction with and introducing compounding errors that way. For temperature, the models actually perform very similar to one another, and there is no evident problem in ForecastNet's temperature. And I have not seen other studies looking into low-level humidity of ForecastNet, so this was a surprising thing to see this comparatively bad performance here, as these models are often introduced as having similar skill. And then if we look at the bias, we can see that this is really a positive bias for the moisture, and this leads to an overestimation of CAPE finally. And it also appears that the diurnal cycle is really exaggerated. And when leafing through the data, this also becomes very evident that relative humidity is too high and it has a really strong diurnal cycle. Yeah, so you have a bad moisture forecast and ForecastNet. You introduce cumulative error by converting that to specific humidity. And as we saw in the beginning, for the parcel profile, it plays a very large role when you switch to the slope of the moist adiabat. So by switching too early onto the slope of the moist adiabat, you will greatly overestimate CAPE in a nonlinear manner, which then leads to these very large errors in, for example, root mean square error. Then finally, we didn't just look at the US, but also at other regions around the globe. Here we see a comparison of North America and Europe. This is now using all initializations of the models, that is 0 UTC and 12 UTC. And the magnitude of the errors is also related to the magnitude of your variables. So CAPE in the US is notoriously larger than other regions. The 300 joules per kilogram threshold we've been using here represents about the 84th percentile in the US, and in Europe and the other regions, it's usually in excess of the 90th percentile. And also we see here in the back the combined variable W max shear, and it is set at a slightly higher threshold, but it largely looks the same as the fraction scale score for 300 joules per kilogram CAPE. So the majority of performance issues stem from CAPE rather than from the shear prediction. And the shear prediction is also the easier forecast problem in the sense and more driven by the large scale features. The bias in ForecastNet is directly linked to the relative humidity issue. We also checked this for the other regions, and it always stems directly from that. And then we also have Argentina and Australia here. Argentina also has a slightly higher CAPE climatology, leading to the elevated errors in the root mean square error. And in Australia, the moisture bias of ForecastNet was actually not that large, so we also see a better performance for CAPE here. Then we also looked at the current operational suite of ECMWF for a single case study, just to get some context on do the additional models, AIFS and Fuji, perform similarly to the others. So here we don't have a full climatology. They've been running since about spring this year. By now we could compute the climatology for this summer at least, but basically we're still just waiting for data to be available. And for a single case study, I would say that these additional models perform quite similarly to the others. We may have similar issues in Fuji as we have for ForecastNet, but one case study is not enough to say that for sure. AIFS seems to line up a bit more with Hydro Weather and GraphCast. But yes, this is not a full evaluation, it's just to put some context that we could expect similar performance from these. So to conclude on this first part, we do see that AI models are capable of producing realistic Cape values and also have a good co-location of high Cape and shear, and the compound variable W max shear also appears to be working relatively well. The more processing steps you introduce, the more errors you will have. So there is an advantage of having models with specific humidity over relative humidity in this case in particular, but ForecastNet has issues with relative humidity in the first place. But this also means that it would probably be better to have Cape as a direct output prediction rather than deriving it from the pressure levels. Then it becomes the question how many variables you want to add, but just as a performance perspective, it would probably be best to do this as a direct prediction. GraphCast and Pango weather are seasonally and regionally comparable to IFS, which we looked at for North America, Europe, Argentina, and Australia. Yes, I wouldn't strongly say that they systematically outcompeted because the interquartile ranges overlap considerably, and if you look at diverse scores, they don't always outcompete IFS, but at the very least, they deliver comparable performance. Then the problem we keep running into with these studies is we're working with kind of extreme events and we have very short time periods for evaluation. So something that would be beneficial for all of these studies is if we have an agreed reference period that is not used in model training that we can use as a hindcast archive for model verification. Even if it's just like 5 years that are not used in model training, but if you, the more you go towards extremes, the more years you would want to have. So for example, for heat extrema, 5 years will still be extremely short. Then we can jump into the second part of the presentation. And here I've been looking into predictability links between heat waves and severe convective outbreaks in Europe, mainly with the purpose of ultimately wanting to extend the predictability timeline of convection. This is quite different from the previous subject, so really hard-cut in subject, and we will here be looking at ERA5 reanalysis and the large-scale processes that relate to convection occurring. This is a project that I pursue with Olivia Matthews and Daniela Domeisen. Yes. A bit of a background on convective outbreaks in Europe. We've talked about this a little bit already in the introduction. They have a high damage potential with wind gusts, hail, and flooding. And what characterizes large outbreaks is that they have a large spatial extent. So when you have storms moving from, let's say, southwestern Switzerland across Germany into the Czech Republic and Poland, this really affects a very large area. And these are the kind of outbreaks that we're interested in. These are often driven by large-scale forcing. They often occur at the leading edge of a trough. So following the schematic here, basically between a low-pressure and a high-pressure system. And at this interface, you often have high Cape values and also high shear, giving you the potential for widespread, very severe and organized storms. And this large-scale pattern should be more predictable than the local thunderstorm. So by systematically tying convective outbreaks to large-scale patterns, we hope to improve the predictability ultimately. We are using here exclusively ERA5 data, so we are working with convection in ERA5, which is not convection resolving nor permitting, it just has a convective parameterization. I'm using the data from 2000 onwards, which is a 1/4 degree resolution. And we define convection through a proxy environment. So for the first part of the study, I'm using a minimum area of 25 grid cells, where 10 meter per second wind shear are exceeded and 500 joules per kilogram Cape. This puts us in the multi-cell range, and then of course can also be higher than that. So multi-cell or supercell is what we are going for to get widespread, moderately organized convection. I also put the criterion that there needs to be convective precipitation somewhere. The convective precipitation scheme is not extremely reliable in ERA 5, so we just say within our target area, it needs to trigger somewhere to indicate that convective inhibition was overcome, there was a trigger present. And I focus on the first day of meeting these criteria, so I want to know how we end up in this situation. And for multi-day events, for right now, we're not so interested in how we stay there. We just first want to know how we get into this situation. And on Cape and Shear, I performed k-means clustering to derive regions in Europe that have convection or a favorable environment on the same day. And this is the map that we see from this. And it also matches our expectations to a certain degree. We get a north-south split that is divided by the Alps. We get this kind of area from Switzerland going through southern Germany into Czech Republic and Poland, which is a known storm track area where you get these really long propagation of storms. You get a north-south divide for France, so intuitively it matches with what we know about storms occurring in Europe. And then by deriving event time series in each of these regions, I computed composites that use the deseasonalized mean of my descriptor variable, and then we can look at the evolution in time of a descriptor variable relative to the target event. We first focus on Central Europe, so this is the reddish-orange region here. Where we find 123 episodes in 22 years, which is about a bit more than 5 episodes per year. This corresponds to 266 convective days, so half of outbreaks are multi-day events. Here we see the duration of the episodes as a histogram, and while half of the events last 1 day, the other half lasts 2 or more, going up and down. And the seasonal cycle peaks in July, which also matches our expectations. We have basically convective activity ramping up sometime in late May and then coming back down in September. For the Mediterranean, there is more of a fall peak in convection as well, but in Central Europe, not so much. Then looking at a handful of composites for this, as a rule of thumb, the convection happens as a progression through several regions. If we have these strongly dynamically driven outbreaks, they kind of move west to east, together with the trough and ridge system they are associated with. On the target event, here we just have the frequency of the convective proxy being met, which situates itself nicely into the Central European region. And on the day of the event, we also see strong anomalies in the geopotential height at 500 hectopascal field. On the day after, we find a strong anomaly in heat wave occurrence downstream of where the convection was taking place. So here for basically off of the Adriatic coast, we get an elevated occurrence of heat wave frequency, which on that day is also right underneath a very pronounced ridge. And we were then thinking about why this could be, because some of the hypotheses are that convection should be the end of the heat wave and basically be causing its demise. And at first sight, this might look contradictory, but I actually think that these things might be complementing each other. So we have the convection taking place at the leading edge of a trough in a Rossby wave train, and convection leads to enhanced diabatic heating through the latent heat release. This can increase the ridge, or basically heat the upper levels of the ridge. On longer time scales, the subsidence can lead to further surface heating, but also you can just stabilize the ridge and allow for greater surface heating without the heat wave becoming unstable. If you consider this being a moving framework, then where the heat wave previously was, you would have the convection then arriving afterwards, and might still amplify the heat wave downstream, but from a Eulerian perspective, the heat wave would come first and then the convection. And in the Lagrangian perspective, which we get more with the composites, the convection trailing the heat wave may interact with it by amplifying the ridge. If if we can frame this as a stable enough framework, ultimately we hope to exploit this because heat waves are the most predictable extreme weather event that there currently is. And if we could translate some of that predictability to convection, we would be very happy. However, we might be looking at the fraction of heat waves here that we cannot predict because they are related to convection. So this we are still working on figuring out, but I think we have some room for hope that we could get some wiggle room here to improve predictions. Looking at a case study for the second half of June in 2021, we had a week of really exceptional convection in Switzerland here, but also going into southern Germany. Yes, there was basically a week-long supercell outbreak ranging from France to Germany during this time. At the same time, around this time, a heat wave started over Eastern Europe and the Adriatic. And a first indication of this heat wave was present approximately 3 weeks in advance, as was already shown in a study by Daniela Domeisen. And this I take as an encouraging hint that we can in fact still predict the heat wave, and maybe we can exploit this information for convection. Because if you get to lead times of 3 weeks in advance, this is basically unheard of for convective predictions. So this is the hope we have here. Looking at this case study in particular and the concept of these composites, we wanted to check that with the composites we are not just blurring signals and creating an artificial dynamical pathway, but that we really find this structure in single events as well. So for the day of June 28, we can really see this widespread convection where the convective proxy is being met, and on the day after, downstream, we see the heat wave criterion being met. Also, we see the pronounced trough that is present on both days that is playing a big role in the synoptic setup here. Then we also flipped the perspective and looked at the heat waves. We have here a heat wave tracking where regionally and seasonally the 90th temperature percentile has to be exceeded for a minimum of 3 days. With this, we obtained 90 heat waves in the Adriatic on average, 4 per year, with the seasonal cycle peaking in midsummer. And 45% of the heat waves in the Adriatic were preceded by a convective outbreak in Central Europe within 2 days. This is a very strict association. It really only allows for the link between the Adriatic heat waves and the Central European convection, whereas in reality this will be a bit more blurry and the dynamic framework would make a bit more sense, but we wanted to first see what we can get with this. And I split these two distributions looking at the heat wave intensity. So we have in blue depicted the maximum temperature of heat waves that are associated with convection, and in gray those without. And these two distributions are statistically significantly different, with maximum temperatures differing on average more than 1.5 degrees, which is a quite sizable intensity difference for heat waves. So we are seeing that the heat waves related to convection are significantly hotter than those without, which may be tied to the additional latent heat release that you get from convection. Then we wanted to look at a few more regions. So now we have basically displayed all of these different regions that we have down here, and the regions that are to the north of the Alps, so the Western European region, Central Europe, and then going towards Eastern Europe, all show this very pronounced wave train. They are marked in the blue boxes here, whereas the countries more to the south surrounding the Mediterranean do show this raspy wave train, but in a much less pronounced manner. And the 4 regions to the north of the Alps also show strong heat anomalies on the day after the convection, whereas those surrounding the Mediterranean do not systematically show this. What I would draw from this preliminarily is that in the Mediterranean adjoining countries, a dynamical pathway to get convection does work, but is not necessary. So if you do have a pronounced trough approaching, this can still lead to significant convection occurring, but the convective environment surrounding the Mediterranean is generally much more favorable than north of the Alps. So this is not a necessary condition to get widespread convection, and you have more options of getting your event, so it doesn't appear as the dominant driver. Then what I'm currently working on, so this is a bit of a more experimental outlook, is that I'm switching this to a dynamical tracking framework where I follow the convective event, and I here follow identified convective proxies with at least 100 grid points, and I apply this to the regions north of the Alps for now. This gives me an event-centered composite rather than geographically fixed composite. As a sanity check, we first see the composite that just has the convective proxy, which nicely centers in the middle, exactly what I wanted to do. Then looking at the heat wave, this is now all on the same day as the event. We do see a downstream elevated heat wave occurrence also on the day of the convection. It is also present on the day after convection, but I try to reduce the time component here for the time being. In the Z500 field, we also see a pronounced trough and a pronounced ridge. The 2-meter temperature shows a temperature anomaly of approximately 4 degrees. The soil moisture anomaly shows a very dry anomaly in the area where the heat wave is. And then where you have the convection, you are basically alleviating this dry anomaly through the precipitation. And then what I also found very interesting is this is the frequency of a low-level warm conveyor belt feature being detected. And approximately in the area of the convection, we have a lot of low-level warm conveyor belt features being detected. So we're also trying to see if the widespread convective outbreaks are basically warm conveyor belts in disguise, but this is really work in progress, and I hope to have more on this in a few months' time. Overall, the dynamical tracking reveals much the same as the geographically fixed composites, which I find very reassuring because they're two quite different approaches. But this allows us to go towards a more general framework that isn't so geographically dependent, that we could possibly apply to more regions than just having a single geographically fixed cluster. This brings me to my conclusions on this. We find that we have dynamically driven convective outbreaks in Europe to the north of the Alps that are tied to a strong wave pattern in the geopotential anomaly and are linked to downstream heat. With heat waves being highly predictable, this may give us the potential to improve the predictability of the upstream convection. And as next steps, I want to disentangle the predictability of the heat wave versus the predictability of the convection. So we want to see if the heat waves that are tied to convection are no longer forecast well, or if we can use this forecast to obtain a better convective forecast. And we are working towards developing a more generalized dynamical framework that has a wider geographical application. This brings me to the end of my presentation, and I would be very happy to take any questions or comments. Thank you very much.
Also from online.
Yes, if there are any questions online, please don't hesitate to ask.
I have a question about you were showing the difference between the convective versus non-convective heat waves.
Yes.
You were showing the distribution. Do you think that there could be also a kind of more large-scale explanation in this, in that maybe the convective ones also have a trough upstream, while maybe the non-convective troughs, the trough ridges.
Yes. So here we cannot yet cleanly differentiate what is exactly the cause of the hotter heat wave. We can see that it is associated with the convection, which is likely simultaneously associated with the approaching trough. And the trough might be the cause ultimately of having the hotter heat wave and the convection, which would also maintain the predictability of the heat wave because the trough should not be as difficult to predict as resolved convection. But yeah, so far we don't have a very clear plan yet how to disentangle these two parts, but what we do see is a very clear association of convection with heat waves and also convection with this very pronounced wave pattern. But we cannot yet cleanly identify the exact process chains, which admittedly is not a trivial task.
Yeah, have you, like, still on this topic, have you tried to plot the heat waves that have convection towards the dirt to see if there's a
I've not split up these two yet, but I did just do composites centered on the heat wave to see where convection would systematically occur. And you do achieve this kind of flipping of, you get convection down upstream of the heat wave slightly beforehand. So this you can flip, but I have not split the composites yet into the two populations.
Am I wrong, or maybe I missed something? Did you check if this what you suppose that convection has an implication on the heat waves is somehow dependent on the severity of the convection?
So here we cannot directly relate to the intensity of the convection because era 5 doesn't have resolved convection.
Yeah, no, but maybe with Cape or with.
It doesn't necessarily directly translate. So it's convective precipitation may be a way because it will direct.
Yeah,
It will kind of link to the latent heat release that era 5 represents. At the same time, era 5 will correct for itself by having data assimilation at some point again, and then nudging back towards the true state. And it really might not have the convective process itself in the right place in the right time. It will have the consequence because of data assimilation, but it might not have the process. So we hope to circumvent this by using the hindcast archetype of ECMWF, where in a forecast run, the model will stay dynamically cohesive. It will not have continuous data assimilation. It just starts from a specific point and runs forward. And if the convective process, which there we can approximate with convective precipitation, just on a surface level, is more or less correct, then we should assume that this latent heat release can for the model is then basically the pathway to get the heat wave. So there we hope to get a better grasp on this and might be able to relate it to the amount of convective precipitation, for example, which should correlate to the latent heat release that the model uses and transports into the ridge.
I mean, another variable that can act as a mediator between the large scale and the mesoscale could be the water vapor transport.
Yeah.
So to be used as indication of the severity of the convection, although it has to be seen, but
in era 5, I'm always a bit hesitant because I'm really not convinced that the convective process is represented well in era 5, but the consequence will be there. We really see that convective precipitation is not in the right place or time.
I also checked that.
Yes, it's yes, and the other issue partially is vertical resolution. So for any kind of direct heating process, we are not quite satisfied with the vertical resolution that we do have. And yes, it's not an easy question at the very least. But we are considering multiple angles of attack to try and get a better grasp on it. For now, we are sticking in the era 5 / ECMWF hindcast framework because then we are not mixing data sources and everything will have the same artifacts. But I was also considering using other data sets to get a more realistic picture. For example, using lightning as the convection definition, and then you can do clustering to define really widespread lightning events, or you could take the flash density as a proxy of the convective intensity, but it may not relate to what ERA 5 has. It should then again have the correct consequence, so yeah. But yes, there is many things that we can experiment with here.
Thank you for the nice presentation. I was wondering if you have seen some links between this enhancement of the heat waves due to convection and the speed at which the ridge is traveling. So let's say the tendency of pressure, maybe if there is some link between these two processes.
So I think for this, I would really need to split it into the different populations. I do have the impression from looking at these time lag composites that are fixed in a geographical location that you have a relatively slow movement of the wave train until it arrives over your event and then basically solves. And we might be able to look at this a bit cleaner if I separate into the persistent convective events, which are most probably related to blocking, so that you are basically at the interface in an omega block between the low pressure system and the high pressure system. The high pressure system is where your heat wave will be, and at this interface is where you continuously get convection. And this was pretty much the case for June 2021. Where Switzerland was having these convective outbreaks, Germany was getting the extreme flooding, and Eastern Europe was under the blocked bridge. But this is then, again, a subsample of these events. And at some point, we also run into sample size problems. So it's a bit the question, do we want to look at the extreme end of convection or the extreme end of convection and persistence? And the more we reduce the sample size, the more we're just looking at single events and not at or we cannot assume anymore that it's necessarily a representative pattern. So another thing I'm doing right now is doubling the ERA5 extraction period so that we have a longer time series and we have more events to play with, and I can subsample the data without losing representativity as much.
Congrats for both of this work. They were impressive, and I remember in March they were only at the beginning, now in middle. So congrats. And regarding, just if I understand well about the intensification of heat wave due to the convection, the interface between the two, the trough and the ridge. So you are proposing that the latent heat release, the upper level, mid-upper level of the troposphere, is moved downstream by the flow, and then it intensifies the ridge at the upper level, and the intensification causes a stronger adiabatic compression, and then an intensification of the heat wave. And then feedback may occur with an increase in cape and so on. This is the process?
More or less. So I mean, it depends also a bit on the timeline that you look at. So on a one-day timeline, you can maybe expect it to amplify the bridge at high altitudes, but it wouldn't have had the time yet to do subsidence. This takes more days. But if you look at long persistent heat waves and blocked regimes of convection, then this becomes plausible, but not necessarily for this one-day delay. So I think there we're really looking at persistent convection and persistent heat wave combinations, which might also be a key to understand why the heat waves become persistent. So this looks an awful lot like the proposed framework how warm conveyor belts drive heat waves. And this is why we were hypothesizing maybe convection is a warm conveyor belt in disguise. So I'm starting to work with the warm conveyor belt data set that has these low-level, mid-level, and upper-level warm conveyor belt objects. But yes, we're really just in the beginning phases, but I did find it encouraging that we do see a spatial pattern that relates to the convection. And then I guess it comes back down to, was the convection in ERA5 even in the right location? And I think if we then go to the modeling framework, we can identify a bit cleaner is the convection part of the warm conveyor belt, basically giving you an elevator type ascent. Yes. And if you can associate this with a warm conveyor belt, this might also give you more legroom for improving predictability, because then you're really just trying to predict the warm conveyor belt in a truck. And considering that in summer we don't have as many pronounced low pressure systems moving through as, for example, in winter, but a lot of the time these systematic outbreaks are tied to exactly that. This might just be what we're looking for this upper limit of really widespread convection. But yes, there's still a lot of things to clarify here. So there's still a lot of hypotheses flying around that we haven't tied up yet.
And can I follow on this? Do you maybe have an idea of like a rough estimate of the heating rate, let's say difference between an outbreak of convection and the warm conveyor belt? So I'm imagining that so a burst of convection, you've got a lot of heat which is released in a short amount of time, whereas in a warm conveyor belt you have a heating which may last for days, and on a larger maybe spatial area. But in the end, what do you think between these two is able to modify, let's say, to have a higher impact on the PV in the upper levels between these two? Do you maybe have a rough estimate?
I really cannot say. Part of the reason why we haven't looked at heating rates for convection is that we suppose in ER5, A, the vertical resolution is kind of coarse, and B, if it's not in the right place, we won't get the right heating rate. We will get the right consequence ultimately, but not the local process. So this is also why we kind of considered doing back trajectories and seeing if they come from the convection, but then rejected it because the likelihood of not finding anything is quite high, and at the same time, it doesn't reject our hypothesis, so we didn't find this the most effective tool. I think if we assume that the convection is a warm conveyor belt in disguise, it basically just gives you exactly that warm conveyor belt process, just with a more rapid vertical ascent than maybe your average winter warm conveyor belt. I think this is also a seasonal difference. A lot of the time, the extratropical storm research focuses more on the fall and winter season rather than the summer, and for good reason.
We see this like when we're looking at convection through lighting in different features of the cycle, and convection is maximized in the warm conveyor belt rather than in front of the front. And we do see these seasonal differences. So that this is talking about Mediterranean cycles. The Mediterranean cycle in and summer or warm seasons are producing more lightning.
And in the end, with this, we're kind of hoping to find a more general formulation how these processes interrelate with one another. So even basically just to find a way to say, okay, this is something that systematically can co-occur together because these separate elements are related to one another. And then we have a bit the chicken and egg problem, which is really the driver here and what is just a consequence. But having this as a working heat wave mechanism can already be very helpful to understand the processes at play. And then, of course, it will not have the same dominance in all regions around the world. So, like for convection in the Mediterranean, it is not necessary to have a wave train to get widespread convection, but it would still work if you have the wave train.
Yeah, maybe it changes in another season.
Yeah, that as well.
Somebody Somebody else have questions online also?
I heard something that there might be in the chat, I think, possibly. I will try to find the chat.
It's on Chrome.
No, I think it's
Okay.
all good.
If possible, I have a question
Yes?
online. Okay, I'm Tino. Hi,
Turn up the
Monica.
volume just a second. Okay, I think we're good. Yes, please go
Okay.
ahead.
Okay, so very good work. Congratulations. I was really impressed by the result of your first part with the model based on AI able to simulate, to forecast instability at the same level of EFS. My question, I'm not sure if I just missed it. Maybe you have already answered, but the audio was not very good. My question is if you have tried to do the same analysis also for the rain field, and in particular during the convective season, because you focused on shear, cape, and also on basic variable like moisture and temperature. But the question is, have you tried to do the same with the rain? And EFS is not the best one compared with GraphCast, for example.
So most of these models don't contain rain. So GraphCast does contain rain, but Kangaroo Weather, for example, does not. And a sneaky hypothesis on why most of the AI models do not contain rain is because they're usually very bad at it, and it's not an easy thing to do. ForecastNet has a secondary model that produces precipitation as a diagnostic variable. But yes, we have not looked at these in this context. And yes, precipitation tends to perform a lot worse on basic variables of state as a rule of thumb from what I've seen from other studies looking into GraphCast and ForecastNet precipitation.
Okay, thanks.
Thank you. And thank you all for coming.
And I think it's lunchtime.
Very nice.